Hello, my name is Adomas Baliuka from the University of Munich, and I'm here to talk about TEMPEST attacks on quantum key distribution modules, in particular our custom-built quantum key distribution sender. TEMPEST attacks are a special kind of side-channel attack. In quantum key distribution, side-channel attacks are very important and must be prevented in order to guarantee security of the quantum key distribution. When a quantum key distribution transmitter is connected to a receiver via a quantum channel, which might be a fiber or free space link, and a service channel for classical communication, the attacker is assumed all power and means consistent with quantum mechanics to attack and manipulate the quantum channel and the messages sent over the service channel. This implies that all quantum degrees of freedom for this qubit encoding must be in accordance to the QKD protocol being used, and the devices must be resistant to, for example, light being inserted into the quantum channel. However, there are more side channels possible if we consider that the attacker might have access to emissions from the devices outside of the quantum channel. For example, on the service channel, not only the messages sent over it can be important, but also the exact timing of these messages and the actual signals sent over this hardware component that constitutes the service channel. And the devices themselves, which are usually controlled by electronics, you will have acoustic vibrations and electromagnetic emissions outside of the quantum channel, classical emissions, that contain some information about the secret key. You can have problems with the random numbers used by the devices. You can monitor their power consumption if you have access to it. Finally, if the attacker has direct access to devices, then security will be compromised. And it is also necessary for quantum key distribution to ensure that none of these side channels becomes a problem, not only the quantum side channels. As we focus on TEMPEST attacks, these are side channel vulnerabilities concerned with electromagnetic emissions, classical emissions, acoustic vibrations, power consumptions, and similar side channels. Over the years, these side channels, in particular the electromagnetic side channel, have been used to attack consumer-grade computer monitors, serial cables, and keyboards, and extract secrets from these devices. Since then, regulations and certifications have been put into place to make sure that consumer-grade devices or devices meant for more security-critical applications don't have such emissions that can be easily exploited. Nevertheless, this field of research is still very relevant today. In particular, recently the use of deep learning methods has made TEMPEST attacks more powerful and versatile. This is because using such methods there is no longer any need for the very complex signal processing required in earlier attacks that you have to do to extract secrets from recorded emissions. And also there is no need any longer to understand exactly which component of the device produce these emissions or how exactly these emissions relate to the secrets. You can simply train a deep learning model, assuming you have control of the device and know the secrets. Using such methods, researchers have been able more recently to extract cryptographic keys from consumer-grade Bluetooth devices via electromagnetic emissions at distances of up to 15 meters. This is because the digital circuit of the device interferes a little bit with the Bluetooth part of the circuit. Also, perhaps surprisingly, consumer-grade laptops have been attacked and cryptographic keys extracted using a microphone, so this is an acoustic side channel, at distances of up to 10 meters. The reason this is perhaps surprising is that the kinds of timescales at which a laptop is operating, for example gigahertz processor speeds, is very different from what kinds of sound usually is able to propagate in air. Nevertheless, when a slightly longer amount of time for measuring these emissions is allotted, the keys can be extracted. And this also illustrates how difficult it is to dismiss such attacks before looking at them as obviously impossible. Our quantum key distribution sender module is controlled by an FPGA, which is used to drive 4 identical pulse generation lines, which create short electrical pulses, which are in turn used to drive 4 different VCSELs that create the 4 different polarization states, horizontal, vertical, plus and minus 45 degrees, that we use for the BB84 protocol. And the pulses are created at 100 megahertz repetition frequency, which is also the clock frequency of the electrical circuit. To measure the electromagnetic emissions from this electronics, we use a magnetic near-field probe, which you can see here. This is basically a coil of wire. And we record these signals only using an amplifier and an oscilloscope sampling at 10 gigasamples per second. And a single trace that we record with the oscilloscope, single measurement, is 2 megasamples, which is enough for 20,000 symbols, where by symbols I mean pulses, and a symbol is one of horizontal, vertical, plus or minus 45 degrees. Let's talk about the attack model. We are using what is called profiled attacks. This means that we assume the attacker is able to buy or obtain via some other means a copy of the device that he wants to attack, and can use this copy to learn what emissions the device emits and what these emissions mean and how to extract the secrets from the emissions. This is called profiling. Finally, in the last step, the actual attack is mounted, and this attack is mounted on a device that the attacker does not control but wants to extract secrets from. And this also means that the attacker only has one chance, what we will call a single trace attack. That is, the secret is only processed by the device a single time. In the profiling phase, the attacker can control what the secret on the device is and can measure the same secret multiple times. In the actual attack, the attacker has one chance to recover the secret from a single trace measurement of the emissions from the real device. And for our measurements, this implies actually, coincidentally, the standard approach used in machine learning for such problems, which means that we have independent measurements for training and evaluation data, which is the data that the attacker uses to profile the device. Training data is used to train the neural network in our case. Evaluation data is used to look if the training is going well. And this is done using key number 1, which is a pseudo-random sequence of 20,000 symbols. The attacker would also be able to change this to a non-pseudo-random sequence, whatever the attacker likes, but we didn't find any advantage in doing that. And finally, the testing, which we derive from all of our reported accuracies and which we use to evaluate if the attack is really successful, is done using a different pseudo-random key, where the attacker has only one chance to predict this key given the measured emissions. And this key is also pseudo-random. Let me remind you, the raw key is 20,000 symbols long. Symbols, it's H, V, P, and M. And it's a pseudo-random key. Now let's look at some raw data. We record a single trace, 2 megasamples, which means that 20,000 symbols is recorded with 100 samples for the duration of each symbol. And we select from this 20,000 symbol long key sequences in the key that look like this, and they differ only by one symbol. And then we find in the recorded trace the time intervals that correspond to these parts of the key and overlay them. This data is not processed other than amplification. And also we add the clock frequency here for reference. You can see that the clock frequency is actually very strongly contained within the signals. And also, despite the fact that in one region of this image the overlaid signals differ, and in all the other regions they are corresponding to the same symbols, you can see large differences between what the signals look like. And also in the middle they seem to be in agreement, despite the fact that this is the only difference. If you want to extract information from this recorded trace, The method we decided on is to take a piece of symbol, such a piece. We decided on a length of 5 symbols and try to predict the middle symbol. So the task is to guess the middle symbol from a 5 symbol long time trace of the electromagnetic emissions. And we will be talking about the prediction accuracy, which means the average success probability of guessing per symbol. Guessing probability of 25% means you have no information because there are 4 different symbols which are equally likely. We do this in order to avoid discussion of basis choice and also in order to avoid the discussion of whether or not the attacker knows the bases chosen by Bob. Usually it is assumed that this knowledge is available. However, this metric is very simple. It's just a prediction accuracy of the raw key. And actually, if the attacker knew the bases, it would be much easier to predict the bits rather than the raw symbols. So this is not this does not make the attack easier. Although here we cannot see a good pattern and we don't know if any information can be extracted, it's also possible to average these pieces. Here we select all pieces which have these symbol combinations in the middle, and then you can see that here the symbols are random. Any kind of symbol is allowed in the average, and that means that we basically get the clock frequency. In the middle, however, we see that the traces, average traces, differ a lot more where the symbol is different than where the symbols are the same. And this is an indication that there is actually information to be gained about the secret key from this trace. To extract this information, we use a neural network, a convolutional neural network, which takes less than 5 minutes to train using 7 measurements. Again, a measurement is a single trace. And we input a 5 symbol long piece of the time trace, that's 500 samples, and we get out 4 numbers which add up to 1, and they indicate which symbol the network thinks was in the middle of this time trace. And the network and also the data that we measured will be released open source, and this is in preparation in order to help other researchers perhaps test their devices and also reproduce our results. Let's look at how effective this attack is. At very close distances from the printed circuit board, such as 0 centimeters, so just a few millimeters away from the board, as well as a few centimeters away, we have almost 100% prediction of the raw key. And this is not only bits, but this is actually the 4 different symbols, because random guessing corresponds to 25%. If the attacker knows the bases, then these accuracies would be higher, and the attack would be even more effective. And you can also see here that at distances of around 9 centimeters, the attack is no longer successful. Also, metallic shielding, assuming it is properly grounded, can mitigate this attack quite effectively. However, one should test if the attack is possible or not. I want to mention something about the amount of training data required for achieving this performance. We used 7 measurements to train at each distance and evaluate it again in a single shot. Here you can see multiple examples of test accuracy. This simply means that we record the test key trace several times, but test on each of them individually. So this is still a single trace attack, but it gives an indication of how stable these results are and what the measurement variation is. In any case, in this figure, you can see that, first of all, having more training data helps improve the attack performance, but starting at around 10 measurements, the improvement is no longer very much. So we decided that 7 is a good number and it's sufficient to demonstrate the effectiveness. And also it demonstrates that data augmentation, which just means using the same training data multiple times, but adding some noise to it and perhaps very slight time displacements of the pieces, is actually very effective and can help mitigate the need for a lot of measured data. And since these measurements take a very small amount of time, taking 7 measurements does also not take a large amount of time. So this measurement can be performed quite easily, and it doesn't require a complicated measurement setup. It can be done basically by anyone. So we also want to look at the near field performance of the attack in different regions of the printed circuit board. As I mentioned, we have here the FPGA, which is controlling the entire circuit, and we have here the part that produces short electrical pulses to drive laser drivers. For our measurements, we removed actually the optical component because it didn't seem to play a very big role. It had very good metallic shielding, and we wanted to focus on what emissions come from the electrical components, because those components are fairly standard and a lot of devices will be using either some kind of FPGA or some kind of different microchip. And basically all of these chips are known to emit electromagnetic radiation, which can be used to infer what they're doing. And if you look at a 10 by 10, 1 centimeter spaced grid, what is our test accuracy for predicting the 4 symbols? You can see that in some regions we are not able to predict above 25%. However, in most regions, and most importantly above the FPGA, we are able to recover the key quite effectively. And one thing that should be mentioned is that not all emissions allow an attack, and some emissions might even make attacks harder. This is sometimes called masking and sometimes considered a countermeasure against electromagnetic emissions, leaking secrets. Here you can see on the left the same figure as in the previous slide that is showing the test accuracy of the attack. And here you can see the root mean squared amplitude in millivolts of the signals that we recorded at each point. And some of the parts of the circuit here and here, for example, actually seem to make the attack less effective because the emissions here are not correlated with the key, and they make it more difficult to detect the emissions that are correlated with the key. In any case, the FPGA is the most vulnerable part of this circuit. Finally, I want to also mention our attempts to measure in the far field. We have a log periodic antenna, and at a distance of 2.5 meters from the device, we try to reproduce all of the measurements you saw previously. We were not successful in getting information about the secret key from this distance. However, we were able to measure 2 different scenarios, which is a much lower bar for a successful attack. Getting the key symbols out is a very difficult attack, you might say, a perfect attack, just to demonstrate that some amount of information is included in the emissions. It's sufficient to be able to reliably distinguish 2 modes of operation of the device. This could be 2 different keys. However, this attack was also not successful for us. The attack that was successful, which you can see the 2 scenarios here plotted in red and blue, this is the spectrum, recorded with the antenna. The 2 scenarios were the device being turned on and sending qubits, and the device being turned on but not sending qubits. And all of these measurements, both the antenna measurement and the near field measurement, were performed and still effective, when effective, in a very noisy office environment. So in the spectrum we have lots of classical communication going on in the background. If we remove these parts of the classical communication and zoom in on some parts of the spectrum, we are able to distinguish these 2 modes of operations reliably and consistently, where we again also have a test dataset, of course, with more than 99% accuracy. And this indicates that even at larger distances, using an antenna, it might be possible to get information from the device. In our case, the attack is not very critical because we couldn't demonstrate any information correlated with the keys themselves. But it might be possible in other scenarios or using different antennas or neural networks, for example. And I want to mention some countermeasures. It is well known in the field of research that is concerned with such emissions, classical hardware security, that measurements and countermeasures against such leakage of information should be performed early in the design of such devices, because fixing such leakage after the fact is much more difficult, and just shielding often doesn't suffice. So in the next revision of our electronics, which we already have measured and repeated all the measurements I showed here, we used a shielding enclosure, which helps a lot, and also a different FPGA footprint, ball grid array, which reduces the emissions from the FPGA significantly. And also we route sensitive signals in inner printed circuit board layers. Also wire placement and capacitor placement can be important. In conclusion, side channels can render quantum key distribution insecure. The research focus has always been quantum side channels, but there are also classical side channels. And while those may not be specific to quantum key distribution and countermeasures are available, these countermeasures affect design decisions, and these design decisions might be specific to quantum key distribution. This means that it's worth looking and considering classical vulnerabilities in the design of quantum key distribution devices at fairly early stages of the design, and also it's very important to keep them in mind when talking about the mode and environment of operation for quantum key distribution devices. This leads us to the questions of whether or not a complete treatment incorporating both classical and quantum side channels for quantum key distribution security is possible, and whether or not classical and quantum attacks should be treated equally, for example, with respect to the abilities that are assumed possible for the attacker. Thank you very much.